This week's topic is, in some ways, one of the most fun topics. It's also one of the more challenging topics for a lot of students, and it's going to be dynamic programming. Now, when you hear the words dynamic programming, you might have the idea when we say programming that it has to do with actually coding, and that's really not where the term comes from. So it's sort of a very weird name, and I wouldn't worry too much about how the name relates to what it does. Just remember dynamic programming, or we'll often just call it DP, just refers to a certain type or category of problems. And specifically, these are going to be situations where you will have a series of repeated subproblems. So something where you are going to repeatedly solve the same subproblem or repeatedly face the same subproblem over and over. And the basic idea of dynamic programming, it's very simple. It just means that you only solve each subproblem one time. So one way or another, you don't want to keep re-solving the same problem. You don't want to, if you faced the problem before, you don't want to redo it another time. Now, there's a couple of ways that we can go about this. I'm going to talk about sort of the two main categories. But the idea here is that if I've got a complex situation, and very often dynamic programming, it tends to be, it doesn't have to be, but it tends to be something where you're optimizing, where you're finding a maximum or you're finding the best or a minimum or something like that. And these types of problems, usually to do that, you have to look at lots of different choices. And then for each of those choices, there's more choices. And for each of those, there's more choices. But in the process of sort of going through and identifying more and more and more and more, you face the same problems over and over and over. And because of that, if you can remember, hey, I've faced this problem before and not recalculate it, you can potentially get a huge time savings. And in practice, dynamic programming can be used to solve a lot of problems that even something like divide and conquer that you think is very efficient, it can even be much more efficient than that. There's dynamic programming approaches that are used to solve sort of limited forms of things that are NP-complete problems. There's a lot of cases where something that is solvable with dynamic programming, you can get things very efficient from it. So there are going to be two main approaches to solving a DP problem. So we'll often just call dynamic programming DP. And the two approaches are a top-down and a bottom-up one. And different people tend to gravitate more to one or the other. I'll just say, to me, I always like the bottom-up form whenever I can use it. It feels much more natural to me. I believe that's sort of the origins of dynamic programming, came from the bottom up. Top down is more of an easy way to add on to what you have. Now, before I go too much farther and go into these two approaches, I'll mention I'm going to just give an overview here, and then I will have a series of videos where I try to break down individual problems and show you lots of examples, because in my experience, the problem that people have with dynamic programming is usually figuring out when can I apply it and how does it apply to a particular situation. And like many things in life, you learn by doing, you learn from experience. So the more problems that you see, the more cases you see where dynamic programming gets applied, you can start to recognize when it comes up in a problem that you're facing. It's not always, it's not just a simple, you plug something into a formula and you're done, or you just, oh, I apply this approach and I'm done. You have to actually recognize, oh, this can be phrased as a dynamic programming problem, and here's then how I might phrase it as one. And once you've done that, after you've figured out how it's a dynamic programming problem, the actual solution is usually not all that complicated. It's the big challenge is usually figuring out how to phrase it. Okay, so the two main approaches, the first one is going to be what we'll call the top-down approach. And you might have heard this referred to memoization. The idea here is that we are going to have a recursive solution. So something where I've got some big problem and I'm breaking that problem into lots of smaller problems, and each of those gets broken into smaller problems. And some of these might, the kind of repeated subproblem, you might actually run into the same subproblems with several different approaches, and then each of those might get broken down into many more subproblems that are even smaller, and each of them might get again reused by multiple versions of the one above it. And so by knowing exactly which things apply to which problems, you can sort of solve things with a standard recursive approach, but not repeatedly calculate the same result. So the idea is you phrase your problem as a recursive problem. Now, normally when you do recursion, you have a recursive call and you have a base case. So the typical thing is you have a recursive call on something smaller, on some sort of smaller set or smaller problem, and you have some base case where you stop. And the one thing that gets added in when you use a recursive approach now for top-down that we are going to add on to all of this is we are going to keep a cache of previously recorded answers. Okay, and so there's a few different ways that you can do this. The idea here is that, the idea here is when you encounter a problem you've seen before, instead of recomputing it and making another recursive call, you just look it up in the cache. So when I face a problem, when I come down, maybe to look at this diagram over here, maybe I've gone through and I've calculated this path previously, the red one that you see there. And then later on, I come and I follow this blue path. And notice I come to the same thing that I've computed there before. I don't recompute it. I say, oh, I've already encountered that. I encountered on the red path. And now when I'm on the blue path, I see it again. And so you don't recalculate. Instead, you just look up the cached results. So a typical way that you might do that is you will often store this in C++, you would call it a map or an unordered map. In Python, it's supposed to be unordered map. In Python, you would just put it in a dictionary, something where you actually associate the input state with the output, and then you look things up. So I'll give you an example of this when we get to some coding problems, the type of thing that we will see in class. But just know that the basic idea here is that we are going to cache the results that we have before so that we look them up later. Okay. Now, the second approach that we have is a bottom-up approach. Okay, in the bottom-up approach, the idea here is you start by solving the simplest cases, and you work your way up to the most complex. So looking at this diagram over here, basically the idea is you would first of all go through and you would solve all of these cases down here at the bottommost level, and then you would go up to this level and you would solve all of those cases, and then you would go up to this level and you'd solve those cases, and then you'd work up to the main problem that you have at the top and you could solve that. And that way you're never going to, anytime you are at a higher level, kind of in this recursive path, I guess you would think of it, anytime you're at a higher level, everything below it has already been computed. And so you're just looking up things that you've already computed. So you never are having to sort of recompute something from scratch. You're just doing the next step and working your way up one step at a time. So bottom up and top down, they each have their own benefits and drawbacks. So let me just mention a couple of them, and then I'll come back and mention a couple more. So generally, if you have something that's top down, so these are going to be benefits, it is the easiest one if you already have a recursive solution. So if you already have a recursion written, say perhaps you thought it was a brute force approach and you just tried recursively generating everything and you realize, wait, this is taking too long, but I have repeated subproblems. I have things where I'm facing the same problem over and over. You can convert it into dynamic programming by just memorizing what's there. So if you already have recursion, top-down is relatively easy to implement. The other thing is if the exploration space is sparse, If that's the case, then this is also a very good method because it means that you don't have to necessarily compute everything along the way. If I go back up to this diagram up here, and I'll use red as an example. Perhaps I explore this red route that I showed before, and on my next path through, I explore this route right over here. And on my next path through, I explore this route right here. But then I'm done. Maybe those are the only ones that I have to actually explore. Well, even though I've got some repeated problems, so for instance, this node right here was repeated in both of those paths, and so I didn't have to compute all the stuff below it. So even though I did have some overlapping subproblems, most of this tree did not actually get explored. So I only explored a few of the routes, and therefore I didn't have to store everything along the way. If I had had a bottom-up approach, I would have had to have first computed everything in the bottom level, and then everything in the one above it, and everything in the one above it, and I would be wasting computation because I'd be computing a lot of stuff I didn't actually need. Okay, so if it's sparse, in other words, if only a few of the paths or only a few of the states are going to be reached, then top-down can work very well. If you have something that is bottom-up, there are some advantages to it. For one, you avoid function calls, and you avoid possible problems with a stack overflow where you've just made too many function calls in a row. So you just made function call after function call, and the call stack gets too big, or it gets too deep, and everything becomes slow. So instead, this is just a bunch of for loops. So all we have really along the way are for loops. It can also, if you're going to have to store everything, so if you have a problem, excuse me, if you have a problem like this one up here, and you really are going to have to store everything in each one of these levels, and the only way you're ever going to get your answer up at the top is to have one way or another computed everything on the bottom, then the bottom-up approach can be more efficient. And it can be more efficient in terms of memory. It can be a little bit more efficient, potentially in terms of runtime, because you're never doing anything wasted. Every single thing you need to compute, you're computing. You can access through the memory. All the memory is stored in one contiguous block, so you're just jumping from one memory location to the next, and it's easier to go through. It can also sometimes, if I think back to this problem that was up here, if I can compute one level and then I go up to the next level, I might only need to keep one previous level. So after I've computed this second level from the bottom and I go up to the one above that, I might be able to throw away all my data from the bottom level and just keep the next one and just keep the next one. So potentially you only have to keep a little bit of the data at the time. You don't have to keep everything from beginning to end. And that can be a lot more memory efficient. So bottom-up can be more memory efficient, and it avoids some function calls. Top-down works better if you have a sparse exploration space, and it's easiest to convert from recursion. So to give you an example of how this works, and this will be one of the examples I code up, you can think of the Fibonacci sequence, and everyone. This is one that is often used for lots of illustrations in computer science, but it works really well to illustrate the different types of dynamic programming. So if you remember how the Fibonacci sequence works, fib of 0 is equal to fib of 1 is equal to 1, and then generally, those are the base cases. Fib of I is equal to fib of I minus 1 plus fib of I minus 2. Okay, so that's the definition. And so fib of 0 and fib of 1 are 1. So in this case, I can compute that fib of 2 is going to be 1 plus 1, which is 2. And I know that fib of 3 is going to be fib of 2 plus fib of 1, which is 3. And fib of 4 is going to be 5, and then fib of 5 is going to be 8, and so on. Okay, so these are kind of the values that we have. Now, if I were going to do this with a top-down method, I would write a recursive function fib, and every time I compute something that that's new, I remember it. Okay, so I sort of have my little cloud of memory things out here, and I know at the beginning that if I have 0, that's 1, and if I have 1, that goes to 1. And so then later on, if I come and I say, I need to find fib of 5, how am I going to find fib of 5? Well, that's going to be fib of 4 plus fib of 3. Now, are 4 and 3 in the cloud over here? No, they're not. I haven't seen them before. So I need to recompute each of them. So let's go to fib of 4. This is going to be fib of 3 plus fib of 2. Neither one of those is over here already. So let's go down here and we compute fib of 2 plus fib of 1 is how I get fib of 3. And now in this case, fib of 1 already exists. So this one right here has the value 1. I already had that right there in memory. That's what that one was. Okay, so I already computed that. So I know that what fib of 1 was, it was 1. Fib of 2 is still not over there. So to get fib of 2, I'm going to have to compute fib of 1 plus fib of 0. Now in this case, both fib of 1 and fib of 0 are over here in this memory. And so I can say that this is 1 plus 1. Okay, and so now I have computed fib of 2. And what I will do is I will enter over here into my memory. I will say fib of 2 has the value 2. So I've now stored that. So now fib of 2 has a value. And I knew that, and its value is 2. And I knew that 2 and 1, 2 plus 1 is 3. So now I know the value of fib sub 3. So I can remember over here, 3 is going to be 2 plus 1. That's going to have the value 3. Okay. Now I come to the second half over here. I need to compute fib of 2. And so I look, and have I computed it before? Yes, I have. I've computed fib of 2. I just look it up. I say that has the value 2. So now I can do 3 plus 2. And that means that fib of 4 has the value 5. And I will remember now 4 over here has the value 5. Okay, and I need to add onto that fib of 3. Again, I look over here, and sure enough, there's where 3 is already defined. It's 3. And so to get fib of 5, I'm going to have the value 8. And as soon as I've computed that, I can also stick 5 over here. Okay, and so at this point, anytime I encounter anything 0, 1, 2, 3, 4, or 5, any of those values, I've already computed them. Okay, so that's kind of the top-down approach. You're still making all these recursive calls, but as soon as you've computed something, you remember what it is so that the next time you encounter it, you know what that is. Now, the bottom-up approach to all of this would just say, well, I know in order to get fib of 5, one way or another, I'm going to have to compute 0, 1, 2, 3, and 4. And so this is where we can just say, so if I'm doing bottom-up, I know that I have fib of 0 is 1 and fib of 1 is 1. And now for 2, I just look at the 2 previous ones. 1 and 1, I add those previous 2 together and I get 2. For fib of 3, I just add the previous ones together, 1 plus 2, and I get 3. For fib of 4, I just add 2 and 3 together and I get 5. And notice that once I've computed fib of 4, I know I'm never after that. I'm never going to need any of that earlier stuff. So I could forget about it. I could just remember the current and the previous one. And that's all that is needed to compute the next value. But then when I come up here to 5, I look at fib of 4 and fib of 3, which I know I've computed them already because I worked from the smallest up to the biggest, and I get 8. Okay, and you can imagine that this is probably actually a little bit easier to implement than the first version, unless you already had a recursive version of the first one. So if you already had a recursive version, you could add on the memoization in the first way, and you could do this one here. Okay, so these are like 2 different ways of doing things. Each one has its own benefits and drawbacks, but that's the basic idea of what dynamic programming is. And to illustrate this, there are a lot of problems that we could deal with. And so I'm going to record each of these as sort of a separate topic, and we'll look at them later more individually. But let me give you a few examples of things that are there. There is something called the prefix sum problem, okay, or prefix sum approach. So a prefix sum is a way of computing ranges and sums over ranges. So this lets us get a sum over a range. And if you remember back when we talked about segment trees and Fenwick trees, that's exactly what we were doing here, except in segment trees and Fenwick trees, the data was changing in the array. This works if you have a static array. But you can also make a little modification to find the max sum over a range. And so I'll illustrate both of those in a separate video. Another thing that you might run into, another type of problem, and it's kind of related to this, there's sort of a 2D version. You can have this in both 1D and in 2D. There's a problem called the longest increasing subsequence. Okay, and the idea here is if I've got a bunch of numbers in a list, okay, something like that. And I want to say, what's the longest increasing set I can get? Well, as an example, I don't know if this is the longest or not, but I can go 1, 2, 3, 5, 6, 8. So that's a sequence 1, 2, 3, 4, 5, 6. That's 6 numbers long. And I don't know, I might be able to get something that's even longer than that if I just picked some different numbers, but that kind of gives you an idea of what an increasing subsequence is. It's like, what's the longest string of increasing numbers that I can get along the way? So that's another dynamic programming problem. I'll show you how to do that. The more general, we talked about coin change when we talked about greedy problems, but the more general form of coin change is a dynamic programming problem. And then there are things like versions of knapsack, of the knapsack problem, which is a nice classical problem, and even the traveling salesman problem, which I probably won't do traveling salesman problem right now. I'll save that for later when we talk about graphs. But I'll try to record some individual videos that kind of illustrate how each of these things is an example of dynamic programming. There's one more thing that I want to mention before we end this part of the talk, and that is that that dynamic programming, the key is usually finding the parameters describing a state. And that idea of a state, if you've encountered state diagrams before, or just the notion of what a state is, this is sort of all the information that describes your current situation. Now, for something like Fibonacci, the state is just a number that I care about. I'm trying to find the Fibonacci value of 3. So 3 is my state. That's not very complicated at all. The reason why dynamic programming problems get tricky and people have difficulty recognizing them is that you need to be able to find parameters that describe a state so that you can write one thing in terms of other ones. So, I can say if I want to find, f for some function f of a and b, okay, if I can write it like this and I can say, oh, it's the maximum over of all of the f of a minus 1 for all the b sub i's, something like that, for all the b sub i's. Okay, so maybe I try every b sub I for a minus 1. Well, if I've already computed kind of this lower value, or if I can compute these lower ones, then I might be able to check every possible b value versus that lower one, and then I just take the maximum of that, and that's my answer for this. Okay, so that just is like the way that you might parameterize something. In this case, you have 2 parameters. You have a and b, and depending on the problem, you'd have to figure out what a and b are. It's not going to be as simple as just a single number. For example, when we do coin change, one of the numbers is going to say which coins have we used, and the other one says what's the amount of money we need to make change for. And those numbers, you can kind of think of them as decreasing or changing. challenging. There's other dynamic programming things where like maybe you have like 5 tokens you can use. And so you sort of have all of your states where you have 0 tokens left, or 1 token left, or 2 tokens, or 3 or 4 or 5. So you've sort of got, these might be all the places you could be, and these are how many tokens you have. And so things would change depending on how many tokens you spent, say, to get through a bus or subway system or something like that. Okay, but the key part, the part that's a challenge, and the reason I'm going to go through some of the examples and show them to you, is that what really the trick to doing dynamic programming comes down to is, can I find the parameters that describe my problem and describe the states that I could be in my problem? And once you can do that, once you can figure out, oh, I can write the problem I need to find f of 2 parameter values, and I can write it as some sort of recursive function like this, where I'm making other calls to smaller problems. As soon as you can do that, usually from there on, it's simple to actually write the code to solve it. The trick is being able to actually generate this type of information. Okay, so look for the other videos that describe this in more detail, and you can watch the class videos where I'll code up a couple of these things just so that you can see them.